All right, welcome everyone to Griswold Controls Actuated Valves webinar. We're excited, everyone that has joined us. We're going to jump right in. 2 weeks ago, in our overview of Griswold Controls product, we looked at all the different ways to control flow, and we looked at the different categories that Griswold Controls makes valves for to control the flow, from flow limiting, manual balance valves, to actuated valves. And this webinar is going to go into greater detail on the actuated valves. So in this rows, you can see we've got actuated control, we've got combination, automatic flow limiting, and actuated control, and then we've got pressure independent. So those are the three categories that we're going to focus on today. So our first category is just actuated control valves. And actuated valves, I don't believe, are the mystery that controls people paint them out to be. I know when Griswold first started 60 years ago, we sold primarily to mechanical contractors. And when we started entering into the actuated valve industry, it seemed like it was this mystery black box of what is happening in the actuated control valve realm. And I don't believe that it's even remotely as complicated as people have portrayed it to be. And so we want to really talk about it down to the basic level and then to the more complex. So actuated valves are really just a valve that controls how much flow goes to a coil or a terminal unit. So each coil would have a control valve. And in this case, we're looking at the Unimizer, which is an actuated ball valve. There's an electronic actuator on the valve that has a motor that basically controls the valve position. So the actuator receives a signal from the thermostat or from the control system, and it basically opens or closes the valve. It can also stop the valve. So in this graph you see on the left side, we've got different colored lines to represent the flow versus the pressure for a valve at different open positions. So for example, the dark blue would be a fully open valve. And so if that valve is fully open, now you can see the flow on the y-axis will increase as the pressure differential changes. The yellow position would be maybe halfway open. And so if that valve is halfway open, now as the pressure changes, you're going to have flow changes. So the valve itself, the flow is going to ride the curve, kind of similar to a pump curve, where you'll get more or less flow depending on your flow rate. So this is the most basic. It's just a simple actuated valve that basically is opening and closing. And so before we look at the Griswold product, we want to look at common actuated control valve types that are in the market. So we've got 4 or 5 different areas that we want to compare. Price, the close-off pressure. So close-off delta P would be how much the valve can close off against without having any leak by. The sizes available, the CVs, the equal percent, and then also the movement, 6-1. I want to point out that Griswold makes valves in the ball valve category, but these don't necessarily apply to the Griswold ball valve. I'm just going to do an overview. So price-wise, typically globe valves are going to be the most expensive control valve, while a zone valve, like an Erie pop top or some of the smaller zone valves, are the least expensive. That's an industry standard. Everyone accepts it. Actuated ball valves were introduced in the late 90s. They were usually on the lower end of the price scale. And then a butterfly valve for larger size would also be on the lower end. The close-off pressure, differential pressure, is the pressure drop that it can close off against without any leak by. So for example, if the valve has a close-off pressure rating of 50, then that means that with an inlet pressure of 50 or less, the valve can completely close and not have any water leak by. Sometimes the close-off rating can be increased by putting a higher torque actuator on the valve. So you'll see that sometimes called out in people's literature, where it has the close-off pressure and then it has a separate section for if they use a different actuator. Ball valves historically have had the highest close-off rating, which all of you should probably be aware of just any of you that have tried to turn an isolator valve that we've shipped that's been sitting for a couple months, it is a very tight fit. A ball valve is designed to be very, very tight and not let any water leak by. So historically, the highest close-off pressure came with the ball valve. A butterfly and a globe valve would be lower close-off pressure. And then a zone valve would be the absolute lowest in the market close-off pressure-wise. There are many zone valves out there that can close off against 10 pounds. So if you're looking at a high-rise, a condo situation where you've got obviously more than 10 pounds inlet to your branches, you're going to not be able to close off, which basically just means you're going to have some leak by. And that may or may not be important, but it's something that is usually called out in the spec what they want for close-off, because there is such a variance in the market. The sizes available, globe valves historically had the broadest size range from 1/2 inch to 8 inch, even higher. Butterflies were typically on the larger sizes, ball valves on the smaller sizes, and then zone valves, same thing, typically on the smaller sizes. The CV and how many CVs there are, a globe valve was designed for the CV that you need. And we're going to look at CV and selection and all of that later. I just want to show the comparison in the market of the different valve types. And CVs for globe valves were typically where you actually wanted to be for a pipe. So if you needed a specific CV for a 1/2 inch valve or 3/4 inch, you generally had that CV available in a globe valve. In a ball valve, traditionally, they were much, much higher. A full port ball valve is actually a very large hole, so you can imagine the CV is going to be higher. Same with butterflies. They also have the larger CVs. And then zone valves have a smaller option. The equal percent, we'll discuss what that means in the next slide, but globe valves by design were also designed to be equal percent, whereas traditional ball valves were not equal percent. Butterflies, same thing. And then zone valves on the market were also not equal percent. The movement in a globe valve is typically linear. It's up and down, whereas in a ball or a butterfly valve, you've got quarter turn rotation. A zone or plug valve, it could be either linear or it could be a quarter turn paddle. So there is a lot of variation in the zone valve style. So we want to talk specifically about Griswold Controls actuated control valves. And to talk about that, the first most important part of the actuated control valve is the equal percentage optimizer insert that is used in our ball valve. But first we want to talk about what does equal percent mean. And the quick definition is when a valve is closed in equal percent increments, so here we're looking at 10% increments, the flow decreases by an equal percent, so it's not linear. It doesn't mean that it increases in 10% increments. It means that the difference between 0 and 10% open and 10 and 20% open has to be the same. So there are many different actual equal percent criteria that you could use. What we have done is our equal percent was to match the coil. And so that's because that is really the reason that you want to be equal percent. If you're looking at a coil has an equal percent characteristic as well, whereas for equal percent changes in flow, you get an equal percent change in the BTU heat transfer. So we know a couple weeks ago we talked about how at low flows, the BTU heat transfer is actually higher, or you get a higher delta T, one or the other. And that's because the fluid's moving slowly through the coil. So you can see, looking at the average coil characteristic graph we have on the right side, when you've got 10% of the ball opening, so you've got a small amount of flow, you have a fairly large amount of BTU heat transfer. And so that makes sense because the water's moving slowly, so there's more time for that water to either release heat or cooling to the coil. And so controlling the valve and controlling the flow in the smaller flow rate GPM is important, because that's when you're having the most impact on the BTU. So having something that mirrors the coil is important, and that's where the Griswold optimizer comes into play. So this optimizer image that you're looking at, the one that's on the far right, would be a ball that if the water's flowing through it, it's fully open. When it's closed, as it's closing the bigger portion first. And so that way your change in flow is much smoother. It's the opposite when it's opening. As it's opening, it opens the smaller part of the ball first, so that point of the triangle is open first. And so that gives you a much finer control, so that if you've ever used a ball valve in the field and you try to rotate it to have less flow or more flow, you'll know how it really jumps around. So this optimizer insert does two things. One, it gives a very smooth flow curve, and two, it slows down or lets less water through as that ball valve starts to open, so that you can have better heat transfer across the coil. The other benefit of the optimizer is it does give the smaller CV. So that brings our ball valve more in line with the globe valve, because like I said earlier, the ball valve has a very large opening, and so the CVs are much larger than what you need for the pipe size. So the optimizer insert does as well give you smaller CVs, and then gives you significantly more CVs than you would have normally in just a traditional ball valve. So this optimizer insert is actually a patented part of our product. And the patent is on the process and the part, and it's a very, very important key part of our actuated control valve product line. So it's in the Unimizer valves, but it's also in the other valves that you'll see coming up, the pressure independent and the combination valve. The second feature in the Unimizer and Atomizer and the pressure independent valves is our low torque seal design. So we talked about this briefly last 2 weeks ago. You can see this black seal, a black O-ring in the middle of this white seal. So there's two Teflon seals on either side of one on each side of the ball, and those close off the ball so there's no leak by. And so it's a very tricky situation. You want to have enough tightness so that you don't have leak by, but you don't want it to be so tight that you need a huge actuator on it to try to rotate that ball. And so that's why Griswold designed our patented low torque seal. So those O-rings sitting behind the seal actually act as like little pillows. And so what that means is a traditional ball valve, as well as Griswold, we require 30 to 35 inch-pound actuator to rotate a 1/2 and 3/4 inch valve. That's very normal. That's kind of what's normal on the market. Ours actually only requires about 20. So we could do smaller actuators, but most of the actuators in the industry start at about 30, 35. But where it's different is for Griswold, for our 1 inch and 1 1/4 inch valves, we're still using a 35 inch-pound actuator, whereas other valve manufacturers in the market have to go to a 75 or an 88 inch-pound actuator. This is a big deal because that actuator is usually 1.5 to 2 times the cost of the smaller 35 inch-pound actuator. So it's quite a jump for your initial purchase cost, and then down the road when you're looking at replacing actuators, because they do wear down before anything else, now you've got an expensive actuator to replace when you could have been using a smaller, smaller, less expensive actuator. It's even more amplified when you go into the larger 1.5 inch all the way up to 3 inch valves. For Griswold, we're still up to 3 inch at a 35 inch-pound actuator, and every other competitor on the market is at either 80 or 88 for maybe the 1.5 inch, but then definitely 2 inch. Everyone's at 120 to 140 inch-pound actuators. And that actuator can actually be 2 to 3 times the cost of the smaller actuator. So your initial investment of product with a standard actuator is going to be higher if you don't have the low torque seal. as well as any replacement cost that you have to do. And since we all know that the actuator is what fails first on any of the valves, you know, that replacement cost is fairly important. The other patented item in our actuated control valves is our repairable stem. So if you're looking at this image, we've got two white Teflon seats on the top and the bottom of the stem. And then we have a EPDM black O-ring, and then we have a groove right here. And some people wonder, what is that groove? Is there supposed to be an O-ring? That groove actually comes from our factory in the valve packed with grease. And that grease protects the O-ring from any chemicals that possibly is in the water that might have made their way past the Teflon seat. And so this is our patented repairable stem, and we launched it in 2007, and I'm proud to say that we still don't really sell any of these repair kits. So it's a very robust design, which is good. We talked about the actuator being the first thing to fail on an actuated valve. The second thing that would potentially fail would be the stem that's cycling. Well, with our stem being repairable, we get rid of the risk of having to replace a valve every time there's a leak. Having said that, because it's so robust, we're not really seeing a lot of, or we haven't seen any stem kits being sold except as spare parts that are being stuck on someone's shelf and probably forgotten. So that is the two other patented items in our actuated valve, and we'll relook at those when we see them come into play in the other product lines that we have. The fourth main feature is our universal mounting plate, and this mounting plate is there, which it allows us to be compatible with the main name brand actuators on the market. We did not want to align up with any specific actuator manufacturer, and so we made this universal mounting plate, which is basically the black parts from the yellow plate up would be the universal mounting. And it's a very, very easy situation. If you want to change your actuator to a different brand, you can't really see the clip, but it's right here, and you can see the screw that's holding it on. You would remove that clip, and then we have clips for all the different actuator brands. So we are compatible with KMC and Siemens, Honeywell, Belimo, Schneider, Johnson Controls, Bray, and Valve Solutions. And I put the first two in italics, KMC and Siemens. Those are the two brands that we actually offer to the market with our valves. But again, any of these we're compatible with, and it is a very simple process to change the actuator in the field. It takes less than 20 seconds. So it could also be, you know, we do offer to install someone's actuator onto our valve, but it's a very easy process if your contractors want to just use their actuators that they have in stock for, you know, other, maybe it's a damper actuator, so maybe they've already got actuators. It was a very easy process for anyone to install one of these actuators. So as you're talking about actuators, I want to talk about the different types of actuation that you see. And this is important, especially for anyone that's doing quotes. I try to include in here all of the different nicknames and shortcuts that people put in. But when you're doing a quote, invariably, they don't use the same words from job to job, engineer to engineer. So as we go over the types of actuation, this is important because it helps you figure out what you need to quote. So there's three different actuator types when it comes to the signal. And so we've got on-off or two-position, and you could see it described either way. I've seen both on-off or two-position in the description on the spec. Basically, it has two signals it receives. One, that it rotates clockwise, and another that it rotates counterclockwise. So basically, the valve can open or close. There's a $1 sign there because it is, historically, it was the least expensive actuator that was on the market. The other type of actuator, which is the most common. This is the one that we see the majority of customers ordering or shipping to us to mount, is a three-state or tri-state or three-point floating. So this one, the actuator has three signals. One signal says to rotate clockwise, one signal says rotate counterclockwise, and a third one that says stop. So the theory is you could fake modulate the system by stopping the actuator at a partially open position. So it's nicknamed the poor man's modulating actuator. But many actuator manufacturers have actually stopped making true on-off actuators. So many people use this as an actual on-off actuator as well. So the actuator performs differently depending on the control system and how it's set up. And when we look at our calculator later, that's a key part. If you're sizing a valve, when you select tri-state or three-point floating, we then ask, are you treating it like modulating or are you treating it like on-off? And this has a $2 sign because historically it was kind of the middle of the road actuator that you could buy. Now that the on-off is going away, with some actuator manufacturers don't even offer an on-off in the most basic option, the three-point is dropping in price, and so the on-off and three-point floating are coming closer to each other. The other type of signal is a modulating actuator. So this one, the actuator has a signal that tells the valve to open or close, and you can open or close it to finite points between fully open and closed. So it's a finer control. It's a more expensive actuator, so that's why it has the $3 sign. If you quote tri-state and they really wanted modulating, then you could potentially be in trouble because of the price jump that you see when you go to modulating. Sometimes they don't call it modulating on the spec. I've seen it also just 2-10 VDC is how they'll basically designate that they want it to be modulating. So modulating or mod I've seen on specs, but then again the 2-10 VDC. But because it is such a big price jump, it's definitely worth paying attention to the signal. The other type of actuation is the power remove position. So the power remove position is when the power is lost to the valve, whether it's through a shutdown or a power and electricity loss. Does the valve stay in place or does it move to some position? So in a fail-safe, it would move to either normally open or normally closed. So if power is removed and it's set for normally open, then the valve moves to open. If it's closed, then it moves to close. So you've got fail-safe and then you've got non-fail-safe. A non-fail-safe, when the power is removed, it just, wherever it was is where it stays. So a non-fail-safe, I put for a dollar comparison, you've got $1 sign versus a fail-safe that can sometimes cost, over twice the price of a non-fail-safe. So there is a big price difference. Sometimes if you're looking at a quote request, it doesn't say fail-safe. It'll say something like spring return or SR for spring return, or it'll say NO for normally open or NC for normally closed. So those are kind of the abbreviations that are used. And if you see a FS for fail-safe or an SR, NO, or NC, those are all basically meaning that it's a fail-safe. So you want to make sure to quote that. And so why do people select normally open versus normally closed? In heating, typically it's normally open because if power is lost in the building, you don't want your building to freeze. So it's going to fail to open so that you still have heat in the building. For cooling, it can really depend on the application. In a computer center, you want it to fail open. So if the power is removed to the coils, then it continues to cool the computer room equipment. And so in that situation, you would want it to fail open. In other situations, you want it to fail closed because you don't need to keep cooling the building unless there's something in there that you need to protect. So it could be either or for cooling. Heating is typically, though, fail open. We did actually look at specs and we looked at how all of the actuator manufacturers were shipping things. Did they believe that it was normally open or normally closed, that kind of thing. And it was about equally split. The actuator manufacturers are kind of doing it both two different ways. So there's really no real industry standard. For Griswold, we do ship in the normally closed position. This is because our low torque seal actually performs better if the valve is left sitting in the closed position. So for Griswold, we will always ship it in the normally closed position if it's fail safe. To change it in the field is actually very easy, and one of those not mysteries that the control people try to paint as a mystery. So if it's shipped in the normally open or normally closed, there's usually a little switch or a little screw right on the cover of the actuator, and it might say clockwise or CW for clockwise or CCW for counterclockwise. It might have a little arrow like a clock actual face, and so you just change the screw to point to that. That's one way to change it from fail-safe to non-fail-safe. One actuator manufacturer, we sell Siemens, and they're fail-safe. If you want to switch it, you actually lift the actuator off of the valve and you turn it upside down, and so that's how it changes to fail-safe. So these two areas, though, the signal and the power remove position, are the most common areas that when you're quoting, you'll be asked for. But there are others. You'll see people ask about the power, and you'll see specs that say 24 volt, 110 volt, or 220. I would say 90% of what we see is 24 volts, so that's the most common power. The speed is another type that comes into play. You'll see speeds anything over 90 seconds up to 110, somewhere in there. So different actuator manufacturers have different speeds. But basically, a slower speed, which would be the 90 to 110 seconds, that means from when it gets the signal to open, it takes about 90 to 110 seconds just to do a full rotation. There are some options for 20 to 40 seconds. We offer some that are about 45 seconds. And those would be used for things like heat pumps, where you really need to get some conditioned water to the heat pump before it times itself out. So the speed, though, is generally the default would be the longer speeds, because people don't like opening a valve quickly and quickly changing the condition of the water in their area. So those are the main types of actuation. Now we want to talk about control valve sizing. And the actuation, we had to do that first because the control valve sizing does come into play when you are trying to size a valve. But I'm just going to talk about control valve sizing. First off, we're going to do it the longer way with the formula, so it makes sense to you. But don't worry, we will, in the end, give you a simpler way and then an even simpler way with our pressure-independent valve. We just want to look at the basic formula here for selecting control valves, because it's good to understand what's behind all of the computer programs and all of the rules of thumb and everything. So this formula can be used for anything, really: components, hoses, coils. I have you guys regularly, or someone's asking me for a pressure drop in a hose or in our isolator S. And so we use this formula to tell you what the pressure drop is based on the flow rate that you're looking at. So this formula shows how the pressure drop across the component is related to the flow rate through the component. And so as the pressure drop increases, the flow rate increases. And we know that as you have more pressure, you're going to have more flow. And we've talked about that last week and the week before. So you're all experts on that already. But it also shows how the pressure drop and the CV are related. So if you have a given flow rate, if you select a high CV, you will have a low pressure drop. And that should make sense, because a high CV basically means a larger hole. Higher CV is a bigger opening, because if you remember our formula from last week, that CV is actually an area value. And so the CV is a value from our test lab, but basically a bigger CV means a bigger hole, and so the bigger the opening, the less the pressure drop is. So since the formula has three variables, if we know any of the two, we can calculate the third by rearranging it. So for example, if we know what the flow rate is and we know what the pressure drop is, we can calculate the CV requirement. Sorry, went too fast. So this sample, so here we've got a sample where we've got a flow rate of 9 GPM and a delta P of 5 PSID. And you can, looking at a coil schedule and the control valve schedule, oftentimes the engineer has detailed what do they want the pressure drop to be. And so in this case, we know it's 5. And so we're going to use our formula. And so the CV is going to be the flow divided by the square root of the pressure drop. So using that, we know that we need a valve with a CV of 4.0. If the exact CV is not available, the rule of thumb is to pick the next highest CV. So we've used to that with our flow limiting valves as well, usually round up. So right there, that's kind of the hint for why you do have oversized CVs or oversized control valves, because there aren't infinite CVs. It would be nice if every CV that was calculated existed. Because of our optimizer, we do have more CVs per size than most manufacturers, because we have the optimizer insert that we could really dial in that CV on our laser machine. So we do offer more, but still oftentimes you're left to round up something. So if the ideal CV isn't available, you're rounding up, and then typically you do provide a valve schedule to the engineer for approval, and so you would calculate what the actual PSID is then from the CV that you picked. So if you didn't have the 4.0 CV and you picked a higher CV, you would then give them, here's the pressure differential, because that engineer, they're approving the PSID, you know, to make sure that they have enough pump head. So here we are we're looking for a CV of 4, and you can see in the 1/2 inch valve, I have a CV of 4.7, and the 3/4 inch, I have 4.3, and in the 1 inch, I have 4.4. So you could pick either of those. There's not much of a price difference between 1/2 and 3/4 and 1 inch. So you could pick based on the pipe size, so you don't have to have any downsizing. You could pick based on picking the least expensive. So there's different reasons for picking, but the goal is you're going to try to pick something with a CV of about 4.0. So now, in this case, we're going to look at a situation where we don't know what the pressure drop is. And this is probably half of the time what you'll be seeing. You'll just get a flow rate. And so we have to use some rules of thumb to figure out what is our CV that is ideal for this situation. So first off, for rules of thumb, we have to look at the rule of thumb for different types of controls, whether it's modulating or on-off. And if it's on-off or tri-state used as a on-off, then basically you just want a low pressure drop. So you can do it a couple ways. If the branch pressure is known, then you could pick a valve that had about 10% of the branch delta P. If the branch pressure is not known, you can pick a valve that's equal to line size and a CV that's in the middle end or on the higher end of the CVs available. Some people say they just pick the highest CV. I don't usually pick the highest CV. I still try to bring the pressure drop to about 0.5 to 1.0. I try not to exceed 1.0. The reason I don't always pick the highest CV available is because I've had too many times where the contractor thought it was going to be on-off. They sized it for that. They picked the highest CV, and then shoot, dang, it's supposed to be modulating, or we need to change something, and they swap out the actuators, and now they've got a really, really big valve with a big opening in it. So I myself try to keep the PSID to between 0.5 and 1 and not go with the biggest CV unless it's justified in the sizing. For modulating control, it's a little bit different. For modulating, you want to take into account what the pressure drop is, because you want, in a modulating valve, you want to actually control the flow below fully open. And the reason is because you want good authority. So authority is a ratio. Basically, it's the delta P across the valve over the delta P of the circuit. So that circuit includes the strainers, the coil, the hoses. And so you want the authority to be about 40% or higher. That's kind of the rule of thumb, is that you want it to be 40%, because if you think about it, what is controlling the flow in a reduced load position? It's going to be whatever is the highest pressure drop. So if the flow limiting valve is the highest pressure drop, it is going to control the flow, and that modulating valve is not going to do anything. Well, by design, our valve actually, as we talked about last week in our balancing, the automatic flow limiting valve, when it's above, or when it's reducing below full flow, our valve drops off so that the pressure differential drops, so that you have that cooperation. So you want the control valve at reduced load to have authority so that it's what's controlling the flow in the system. So you have two things that you could do. If you know the coil delta P, which oftentimes that's on the schedule, you can pick a control valve that's at least equal or greater than the coil. Because if you're greater than the coil, then that means at reduced load, as your valve is modulating closed, it's going to have more pressure drop. And so it will therefore have a higher pressure drop and have authority and control out higher than the coil would. If the coil is not known, then the industry standard is just to pick between 3 and 5. Johnson Controls in their valve sizing books, they say up to 7, even up to 10. So there are a lot of rules of thumb, and it is dependent on the area. But 3 to 5 is kind of the overall, the most common rule of thumb that we've seen. So sometimes people think, well, if I want authority and I get more authority having the highest pressure differential, then why don't I just pick a high pressure differential? Like, isn't that a smart solution? And the reason that that necessarily doesn't work is because of cavitation. So cavitation is what happens when the fluid in the system vaporizes, and it specifically happens as it's going through a smaller port. And so as it's going through the smaller port and vaporizing, it can make noise, it can damage the valve. And so if the delta P is too high, then the outlet pressure may be lower than the vapor pressure, and then you're just more at risk. So a conservative guide is you want your allow your pressure drop across your control valve to be less than half of the inlet pressure minus the vapor pressure. And so that's in our sizing guides, we publish that formula. So that explains why you don't necessarily want to just pick a high pressure differential, though, so that you have the ultimate control. So now if we're going to look at this, we had a 9 GPM requirement. And so we know that it's modulating. So if you look at our literature, you will see, I'll just explain the literature to those of you that are here. So this data in this text of the table is the flow rate. The CV is equivalent to the flow rate at a 1 pound drop. So that is this column here that has the black box around it that says CV. So that it's dual purpose. You see the CV of the valve, but you also know at a 1 pound drop across this valve, that's how much flow you have. So for the first valve that we make, has a CV of 0.38. At 1 pound drop, you have 0.38 gallons per minute. At a 3 pound drop, you have 0.7 gallons per minute. So that's how you read this chart. And typically, like we said, 2 position, we put those on the left side where you've got the 0.5 and 1. So most of the 2 position, you want to find your flow rate in there, and modulating, you want to come here to between 3 and 5. So we're looking for 9 GPM, and we can see that We have a CV of 4.7, and so we'll be somewhere between 3.5 and 4 PSID to get 9 GPM. Same in the 3/4 inch size, we can find the 9 GPM and we can know that it's right about here in the middle. And so you can see we're still back with that 4.7 CV, 4.3 CV product, and that's by using the table, just knowing that for modulating, you're going to try to, for most part, staying within these columns for modulating. Have I seen it go up to 7 in some applications where they want more authority? Yes. Have I seen it go to 2.5 or 2 where they, there's just maybe the flow rate is not available in the modulating? Yes. And so that again is where the valve schedule in Quick Quote, where you're filling it out, you can actually create the valve schedule, and that's what gets submitted back to the engineer, and they'll say, okay, at 9 GPM, I'm going to have 3.7 or something PSID. Is this approved? So this is using the literature and the rules of thumb to size it. No formulas required, just using the literature. Now, the easiest way is, of course, to go to some calculator. So we have the calculator on the phones. We have the calculator on our on the desktop. So this is a screenshot of the calculator on the desktop. You can see we put the guidelines in about rules of thumb. We also put in about the risk of cavitation, and so we put in the vapor pressure chart. So you can use this calculator. You enter in the flow rate. You pick that it's a Unimizer 2-way, and then you put modulating. If you had picked the tri-state one, it would have said, okay, it's tri-state, but is it modulating or on-off? And then we have the stoplights that give you, as you pick the valve in step 3, as you pick the valve, it will give you a red light, a green light, or a yellow light, and give you advice. Pick a higher CV, pick a lower CV. So you can see we're back with this same 3/4 inch 4.3 valve that we saw right here in this slide. We pick it there, and now we can see that if we use that valve, our actual valve pressure differential, actual pressure drop across it is a 4.38. So you can also put in the branch pressure, delta P, and calculate what the authority is. So it's a simple tool. We have added in the calculator portion of this into Quick Quote. So if you're in Quick Quote and you pick a Unimizer and you don't know what CV, there is the calculator built into, it shows up on the bottom right hand of the screen. You put in your flow rate of 9, and it gives you all of the pressure drops at each of the CVs, so you can pick your CV accordingly. This calculator, though, and the iPhone app and the Android app, they have the stoplights to try to help you get to the best solution and the best selection. So that is valve sizing the easy way. Before we talk about valve sizing the easiest way, I want to just talk quickly about the combination valves. We've got, this is showing the atomizer. We've got the balance zone as another combination valve where we've got the flow limiting cartridge, and then we've got the actuated ball valve. So on the right side, you see the low torque seals, the repairable stem, the optimizer insert, all in this Unimizer portion of this atomizer, and then the flow limiting valve. So in our actuated valve product line, we do offer these combination products where you've got all of it built in, all of the return side of the coil built into the package. So all the benefits of the Unimizer with the flow limiting cartridge. I want to talk mostly the rest of the presentation about the pressure independent valve categories. So if you look at these two graphs, we looked at this quickly in our first webinar of the Griswold overview, but it's worth repeating because it's the pressure independent category is a newer category in the industry, and so I think it's worth the explanation. So if we're looking at pressure independent valves, we've got a graph on the right side, which is a traditional actuated valve. So that's what we just looked at with the Unimizer. And like I said, the blue line would be fully open, the yellows may be halfway, and so the the flow rate is going to change as the pressure changes. That's one way the flow will change. The other way is as the ball position changes, or the globe, or whatever the actuated valve is, whatever style it is. So as the position changes, you'll have flow changes, and then once the position is set, you'll have changes if the pressure differential changes. For a pressure independent valve, that's the graph on the bottom on the left, we've got different colors again representing different, for us, for Griswold, different ball positions. So the turquoise blue would be fully open, yellow would be in the middle. And so the valve's going to modulate based on what the zone needs. So if the zone needs less flow, it will modulate closed. If the zone needs more flow, it'll modulate open all the way to, the full open position. But unlike an actuated valve, once it's done moving, if there's a pressure change in the system, you will still remain constant flow. So that's the graph. We've got the graph is now horizontal. As the pressure changes, you don't have any flow changes. So it's almost like putting in the Griswold automatic flow limiting cartridge at each specific flow rate below full open. And so this is important for pressure independent valves because they have almost infinite CVs or infinite high limit flows, where as it's modulating below, it needs less flow, you still maintain constant flow when the pressure changes. And we talked about how often the pressure changes last week in our automatic balancing presentation, because every time someone in some other part of the building changes something, you change the pressure dynamics in the overall system and to every coil. And so if in a traditional system, now that actuated valve would have to rotate to some other position, whether it's more open or more closed. So it's going to cycle. And as it's going to cycle and try to get to a new set point, to get basically back to where it was already satisfied. The zone was good. It didn't need to change, but because the pressure changed, now the actuator has to rotate. With the pressure independent, you save on actuator cycles because now when there is a pressure change, there is no flow change. So there's no need for the valve to cycle until you actually change the load in the room. And so the pressure independent valve is the next level of actuated control valves because it gives you all of the flow limit control below full load. So how does the pressure independent valve work? It's a little bit different than the Griswold flow limiting cartridge. Most of you are used to, there's some flow limiting cartridge that is set at 4 GPM or 5 GPM, and it maintains that at 4 GPM, as long as you're at full load. And then at reduced load, the actuated valve is going to take over and it's going to modulate below, and the cartridge is just sitting fully open. In the pressure independent valve, there's a pressure regulator. So this is an image of the PSID valve. And the pressure regulator's on the left side. There's a diaphragm inside. There's a spring inside also. And the purpose of the cartridge in the pressure independent valve is actually to maintain a constant pressure drop across the control valve. So here, if you're looking at this, you'll recognize the ball with our optimizer insert, our low torque seals. So the PSID has all the benefits of the Unimizer as well built into it. But just like in an actuated valve, we know as you increase your pressure, you change the flow. So the goal is, how do we keep that from happening? Well, this pressure regulating diaphragm cartridge maintains a constant pressure drop across the optimizer or across the actuated ball valve. Same principle in our other valves that don't use a ball, like a globe style in the MVP, where the pressure regulator is actually maintaining a constant pressure differential across the flow control device. So the control of the flow itself is actually coming in the PSID from the ball. So the ball is actually set at 4 GPM, 3 GPM, 2 GPM. Those are the increments when you're ordering it. And the cartridge itself is just maintaining a constant pressure differential across that ball as there are changes in the system. So that's the pressure independent valve, how it works. Within our pressure independent category, we have the PIC-V, which is the cutaway we were just looking at. It's shown right up here as well. There's the space saver version that does not have an isolation handle, and then there's the full PIC-V version that has the isolation handle. We also have the Pinnacle, which is more of a zone style pressure independent valve. Remember we talked about the zone valves, they didn't have as high of close-off pressure, and so the Pinnacle is a zone type valve, so it has a little bit lower close-off pressure than the PIC-Vs, still better than most zone valves on the market, but it brings it more down to the zone style. And then we've got the MVP, which is shown on the bottom right, and then the PIM-V valve. And so they all have the same function where there's some pressure regulator maintaining a constant pressure differential across the actuated portion of the product. So now we look at valve sizing. This is the easiest way. We said, you know, doing it with formulas is the old-fashioned way. Doing it with rules of thumb and calculator is definitely easier. And for pressure independent, this is the absolute easiest way. Oftentimes it's said, you know, pressure independent valves, you don't even need to do any CV selection or anything. And so that's why it's the ideal actuated valve. Now, I've already shown you how actually easy it is to select a CV. So now you know when they're saying how hard it is, and that's why PIC-Vs are the best, because you don't have to size it. You know it's actually not that hard, but this is the absolute easiest way. You want to know what is your coil flow or what is your terminal unit flow, and then you pick a PIC-V valve that has that flow. So if it's 3 GPM coil, then you pick the 3 GPM PIC-V. If the exact flow isn't there, then obviously you round up. So if they wanted 3.5, we don't have that, so you would pick the 4.0. So you don't need to do any CV calculating at all, so that's why it is definitely the easiest one to size. There are customers, and some of you have contractors that actually just pick the biggest CV, or the biggest GPM anyway. So for example, in this first row, we have a flow rate of 1, 2, 3, 4, 5, 6, and 7. And that basically means it's a different optimizer, right? So the 1 GPM has a small optimizer with a smaller hole. The 7 obviously has a big one. There are contractors that just make their life simple, and they say, we want them all at 7 GPM. And then for the coils that are 3 or 4, they use our table, and we say, okay, at 50%, that 7 GPM is actually at 4. At 60%, it's at 5. You know, so we have a table. So you could even make it even simpler, where you just buy only one. And there are some contractors that have done this, and then they use that table and they set the valve in the field by basically limiting the actuator so that it doesn't go past the flow rate where they want it to be. So you could make the overall job easier by doing it that way, but then you are still having to set it up in the field with the contractor. But valve sizing wise, this is definitely the easiest way and the easiest to size. I'm going to move now to the next category, which is the pressure, using the pressure independent valve in our EPIC system. And so historically, we said you want to control your delta T by controlling the flow. And we talked about that last week and the week before so much that you're probably all tired of it. So we know that controlling the delta T is very important. And so if we can directly control the delta T, the temperature drop across the coil or the heat transfer equipment, if we can control that delta T, then we don't have to control the flow. And if we can optimize that delta T, then we can pump less water. And so pressure independent valves evolved into a temperature independent system. So if you're looking at our EPIC system, the PI in EPIC is red because it is a pressure independent valve based system We take our pinnacle in the smaller sizes and our MVP valve in the larger sizes, and we build around that a system to directly control the delta T across some heat transfer equipment. But the heart of it is still the pressure independent valve. We add in temperature sensors. There's a sensor on the inlet to the coil or the terminal unit, and there's a temperature sensor on the outlet. That is where we're measuring what the delta T is. There are pressure sensors before and after our pressure independent valve. That's how we know that we're within the pressure range, and that's how we know what the flow rate is. Because the valve itself has the ability to know what the flow rate is, it has a built-in flow meter. And then from that, you can calculate your BTUs. So it has a BTU meter, and it is all Bluetooth compatible. But the important thing is that it is built around the pressure independent valve, and now taking you to the next level of temperature independence. So how does EPIC work? Well, the EPIC system measures the energy usage while monitoring the coil performance, really. So it adjusts the pressure independent control valve to optimize your coil's performance. So each coil has an optimum delta T, that's the temperature drop. The coil manufacturers, boiler, everyone that does some kind of heating or cooling has an ideal delta T. And so the EPIC system adjusts the pressure independent valve to optimize that coil performance. So the PI, the pressure independent valve, maintains the correct flow, obviously, in spite of pressure changes. And that's one thing that our unit does that other competitors on the market that are not pressure independent. So that way you're only getting a flow change when there's a demand change or when the delta T is outside of the specification. So the EPIC controls the valve based on the delta T. So the temperature sensors are measuring the delta T across the coil. So the EPIC controller, the brain, which is shown in this box behind the MVP, it knows to open or close the valve based on the delta T requirements, right? So we know that if you need higher delta T, you need to slow down your flow. So if your delta T is too low and you want to raise that delta T, you actually need to close the valve a little to slow down the water. And so the valve will be opened or closed based on how to dial in that delta T to get to that specific delta T requirement. When the load changes, so that's a different situation. When there's a load change, maybe there's more heating or cooling requirements, there's some thermostat on the wall, it's going to sense the load change, or the building management system. And so when the thermostat is adjusted, it's going to change the coil's, airflow. And as that airflow changes, the delta T of the water changes. And so again, that's what we're measuring. And so the temperature sensors read the change in the delta T, and the EPIC brain, the controller, controls the valve to adjust the delta T back to the design. So the thermostat is actually not controlling the valve. The thermostat is controlling the coil, and then the coil is then impacting the delta T, and then the delta T in sensors read that, and as they read that, then they adjust to correct the delta T. So the EPIC system is really the next phase in evolutionary, for control systems, and we do have a quick little 10-minute video about that. We're getting close to time, so I'm going to try to wrap up. If you're connected to the EPIC controller, you can read the data in your BMS system, but you've also got the ability to look at it on your iPhone app. So you can see the return side and the supply side temperatures, the delta T, the pressures. You can see your target delta T. So all of that is available for data collection either through the building management system or into your phone. And I know all of you are wondering about BACnet. We are hoping to have a late summer launch of the BACnet version of the EPIC system. So that is the overall Griswold product line with the actuated control valve. And we looked at the unimizers and the basic actuated control valve, the combination, which is the atomizer, and the balance zone, and then the pressure independent valve. So I thank you all very much for joining us. I know everyone's busy, so we appreciate you taking time out of your day to join us, and have a great day.